Growth is all around us. And when time-lapse photography speeds up the passage of time, the process of growth takes on an almost magical quality. Growth sometimes happens in a regular, steady fashion. With each day or week or month, a fixed amount of growth is added, whether it's the growth of a plant or a person. It's this kind of growth that we'll look at in this unit. We'll see that when we plot regular growth on a graph, we get a straight line. We'll learn that straight lines can be described with the general equation y equals mx plus b. And we'll learn how to use either the graph or the equation of a line to predict a future value. In Wonderland, Alice stumbles on a magic potion. One sip, and she grows, and grows, and grows. Alice gets into some tight squeezes. This kind of magic growth potion is fantasy. But in real life, there is a substance that can make people grow larger, and it's an important medical treatment. Sarah seems like a perfectly normal, healthy young girl.
No, too late! I hit the base! I hit the base!
But during Sarah's early childhood, her mother noticed that Sarah wasn't growing as quickly as other children her age.
This is her kindergarten class. She was 5. You can see here that she's a lot smaller than everybody else.
To see if there was really something wrong, her doctor charted her growth with a graph.
I really hadn't noticed this until I just looked now.
It's common practice to put time on the horizontal scale. Here, that's Sarah's age in years. We put her height in centimeters on the vertical scale. Now for the data. When she was 3, Sarah was 85 centimeters tall, so our data point goes here. At 4 years of age, Sarah was 90 centimeters tall, and so on. Sarah is growing steadily. In fact, the points lie close to a straight line. That shows that Sarah is adding about the same amount of height each month. This is an example of the kind of straight line growth we've been talking about. A fixed amount is added in each time period. But how does Sarah compare with other children? To find out, we can add a line on the chart that represents the median height of all children. Of course, not everyone is the same height, so doctors add colored bands on either side of the median line to represent the normal range of heights. This area captures 90% of the population. Very tall and very short children will fall outside these lines, which is exactly where Sarah's growth points lie. We can see that the line representing Sarah's growth is unusual in 2 respects. First, it falls well below the normal range. This means Sarah is short for her age, which is not in itself a cause for alarm. The real problem with Sarah's growth line is that it's less steep than normal. The steepness of a line shows the rate of growth, how much a child grows in a given period. Steep lines show fast growth, while shallow lines show slow growth. Later in this unit, we'll learn a way to precisely measure this steepness. For now, we can say that the steepness of Sarah's line is 4. She's growing about 4 centimeters a year. But the steepness of the median for all children is about 6 centimeters a year. Sarah is falling further and further away from the normal range, and that's troubling.
Think you've grown? Think so?
After extensive testing, the doctor discovered that Sarah's body wasn't producing enough of a substance called human growth hormone. Luckily, scientists have figured out how to make artificial growth hormone. Sarah began getting regular shots of this artificial hormone.
Okay, Sarah, let me get you a shot.
Getting a shot isn't fun.
Okay.
But it's Sarah's only hope of attaining a normal height. After Sarah started treatment, she started growing faster. Her growth rate increased dramatically, which can be seen on the graph. The steepness of the line after treatment is greater than that of the line before treatment. In fact, it is greater than the steepness of the median line, which means Sarah is growing faster than her peers, and will soon be back in the normal range.
An average untreated patient with growth hormone deficiency will wind up in a height area of 3.5 to a little over 4 feet tall, whereas we are projecting that Sarah's final adult height will be over 5 feet tall. So she will have a dramatic response to growth hormone as opposed to what she would be untreated.
Human growth hormone is no magic potion. It can't make all short people taller. Just those whose natural supply of the hormone is low. But for Sarah, the treatments mean a return to normal growth. Straight-line relations like the one describing Sarah's growth can be found in a remarkable number of situations. For instance, let's imagine something completely different. Ticket sales for a new blockbuster movie. Again, since we're talking about change over time, we put time in weeks on the horizontal scale. Ticket sales in millions are on the vertical scale. In the first week, about 500,000 tickets are sold, so here's our first point. After 2 weeks, ticket sales total 950,000. Like Sarah's height, ticket sales show an overall straight-line pattern. Now, we'd be surprised if the growth of movie ticket sales was exactly straight line. It's normal for data to be somewhat irregular, and sure enough, no straight line passes exactly through the points on our graph. Nonetheless, we can fit a line to this data, a line that describes the general pattern of ticket sales. We can do this by eye. Just draw a line that is close to all the points. Some of the points will lie a bit above a fitted line, some below. But the line is still a good general description of how ticket sales are increasing with time. Computer software lets you find the line that is closest to the whole collection of points. But drawing a line by eye does a good job when the points fall roughly in a straight line as they do here. Representing straight line relationships with a line on a graph is very useful. It lets you see the overall pattern, and it can give you a good idea of what a particular vertical scale value will be for a corresponding horizontal scale value. But even more useful would be an equation that describes the situation. Fortunately, all straight-line relationships can be described by the single general equation y equals mx plus b. The x represents the variable on the horizontal, or x-axis. Here, that's time. Y stands for the variable on the vertical, or y-axis, number of tickets sold in this case. The two constants, m and b, give us a specific straight line. B stands for the y-intercept, which is exactly what it sounds like. It's the place where a line crosses or intercepts the vertical axis. Another way of saying this is that the y-intercept is the value of y when x is 0. It's not surprising that for this line, b equals 0. That's because when the movie is released, that is, when time is 0, no tickets have been sold. The other constant, m, describes the steepness of the line. This steepness is called slope, and it says how much y increases when x goes up by 1. Another way to say this is that the slope is rise over run. Run is the change in the x value, and rise is the corresponding y value. So the slope, or rise over run, is the rate of change in y. In this case, our change in x is 3 weeks, and the change in y is 1,500,000 tickets. So the slope is 1,500,000 divided by 3, or 500,000. That means that about 500,000 tickets are being sold each week. Now we have what we need to formulate the general equation of this line. We replace m, the slope, with 500,000, and we replace b, the y-intercept, with 0. So the equation of this line is y equals 500,000x plus 0. Now, suppose we had to work the other way around. Suppose we had the equation and needed to draw the line it described. We can do that by taking advantage of the fact that 2 points completely determine a straight line. We can use the equation to find such points. For instance, let's choose 2 values for x, say 1 and 5. The equation lets us find the corresponding y value for each x value, which in turn gives us the coordinates of our points. When x is 1, y is 500,000. So that's this point here. And when x is 5, y is 2,500,000. So that's this point. Now we can draw a line. Both the graph and the equation remind us of the basic nature of straight-line growth. The same amount is added in each time period. The slope is just the amount added in one time period. An important reason to fit a line to data is to do prediction. Sarah's doctor could predict from Sarah's steady but slow rate of growth that her future height would be much shorter than normal.
Closer to the normal range.
Likewise, based on the new line describing her growth after treatment began, he could predict that Sarah would soon be well within the normal range of height for girls her age. We can do the same type of thing with our graph of ticket sales. We can predict from our graph what the total will be after 10 weeks. Starting from 10, our X value, we go straight up to the line, then over to the ticket scale. Here's our prediction. 5 million tickets will be sold. The equation of the line makes prediction even easier. Just substitute 10 for X and do the arithmetic to get the predicted value of Y. We get 5 million once more. Prediction of a Y value for a specific X value that lies outside the range of X in the original data is called extrapolation. Extrapolation is a useful tool, but it has to be done carefully. For instance, what if we tried to predict ticket sales after 10 years? That's 520 weeks. Using our equation, we predict that the movie will have sold 260 million tickets, one for almost every person in the United States. But that's not very realistic. It's ridiculous to imagine that ticket sales will continue undiminished for 10 straight years, even for a blockbuster hit. Using extrapolation to make predictions has to be done carefully. You can only rely on the fitted line as long as the conditions that produce the initial data don't change. In fact, conditions usually do change. For instance, here is a graph of the median height of women for the first 25 years of life. You can see that from about age 2 to 12, growth follows the kind of straight-line pattern we've been working with. But then, growth levels off. This is an example of the kind of changing condition that makes extrapolation tricky business. In this case, of course, it's good that conditions change. Otherwise, we'd all end up like Alice. In this unit, we've learned about straight-line relations. We've met the general equation that describes all straight lines, y equals mx plus b. And we've seen that fitting lines to data is useful because it can allow us to predict future values, provided the conditions of the situation don't change.